Okay, section 5.1. Okay, when we evaluate definite integrals later on in this chapter, we will often be finding the area under a curve, which means the area of an enclosed region between the graph of a function and the x-axis. So I showed you a general example here below. So this is just a portion of the graph of some function f of x from x equals a to b. So if you shade between the curve and the x-axis, you're going to get a region that looks something like this. Now, clearly, the area of the shaded region cannot be found using any formulas from geometry. So we are going to need calculus to find the exact area of that region. And that's going to be later on. But for today, we're going to start out by finding the approximate area of such a region under a curve. And we're going to do this by breaking up the area into several rectangles, finding the area of each rectangle, and then adding up these rectangle areas. So here's an example. I want to sketch and shade the area under the parabola f of x equals x squared from x equals 0 to x equals 1. So all I did is graph the function. There's the parabola y equals x squared. I'm going from 0 to 1, which gives me that region right there, again, which looks like that. Okay, now I want to approximate the area using what we call an R4 right Riemann sum. Now let me explain what that means. The 4 means we want to use 4 rectangles, and the fact that it's well, first of all, a Riemann sum is just a sum of rectangle areas. Okay, so Riemann sum is just rectangle areas. And the right means that we're going to use the right endpoint of each subinterval to get the rectangle heights. And again, on these we're going to use equal width subintervals unless you're told otherwise. Okay, so here's how it's going to go. I'm going to break up the region from 0 to 1 into 4 equal subintervals. And so when we do that, you're going to see that they're each a quarter unit wide. Okay? And so again, I'm just splitting it up into 4 equal subintervals. And then what I'm going to do is, for the first subinterval, I'm going to take the right endpoint, follow it up till it hits the curve, and then go straight across to draw a rectangle. So there's my first rectangle. I'm going to do the same thing in my second subinterval. I'm going to take the right endpoint, since this is a right Riemann sum, follow it up till it hits the curve, and that's going to be my rectangle height. And so I go straight across and down. Okay, same thing with my third subinterval. Take the right endpoint, follow it up till it hits the curve, use that as the height of the third rectangle, straight across and down. And then same thing with my fourth subinterval. Take the right endpoint, follow it up till it hits the curve, and use that y value as the height of my fourth rectangle. And so you can see that I've got these 4 rectangles right here. And by the way, as you can see, what I'm going to do now is I'm going to take these 4 rectangle areas I'm going to find those 4 rectangle areas and I'm going to add them up, and that's going to serve as an approximation for the area of this region right here. Okay, so clearly all 4 rectangles have a width of 1/4, and now let's look at the heights. This first rectangle height is the y value when you plug 1/4 into the parabola function. So in other words, the first rectangle height is f of 1/4. Okay, and then obviously the second rectangle height here is f of 1/2, which is f of 2/4, right? And then the third rectangle height here is f of 3/4. And then finally, my fourth rectangle height is f of 4/4, or in other words, f of 1. Okay, so I'm going to put all this together. Okay, so I'm going to find those 4 rectangle areas and add them up, and that's going to serve as an approximation for the area under the curve. And again, I just want to make a note about the fact that the widths of the rectangles or subintervals are all 1/4. And one way we can get that is by taking the total interval width, which is your b minus your a, which is 1 minus 0, which is 1, and then divide by the number of rectangles, n, which in this case is 4. And so that's another way you can get the width. Okay? You could see it on the graph, but this is mathematically how I can get that width of each subinterval or of each rectangle. Okay, so the area under the curve can be approximated by taking the 4 rectangle areas. So there's rectangle 1 length times width, rectangle 2 length times width, and so on. And again, all the widths are going to be 1/4. Okay, now what about the first rectangle length or height? Well, again, that is f of 1/4, as you can see. Right here, f of 1/4, which you can get by just plugging 1/4 into your function y equals x squared. And so 1/4 squared gives you 1/16, and then 1/16 times the 1/4 gives you that. And so that's the first rectangle area. Okay? Okay, then you go to the second rectangle. This is the second rectangle height, f of 1/2, which again, you just plug that into the function, which is 1/2 squared, which is 1/4, and 1/4 times that 1/4 gives you 1/16 as your second rectangle area. And you just keep doing this. Here's the third rectangle height, f of 3/4, which is 3/4 squared, which is 9/16 times the width, gives you 9/64, and so on. And so after that, after the fourth rectangle, I get that area, I get a common denominator, I add them up, and you get 34ths, which if you change to a decimal, you get 0.469 square units. Now, very important, this approximation is greater than the actual area, as you can see, because the rectangles are circumscribed. In other words, they go above the shaded region. Okay, so I mean, you can see that when you add these 4 rectangle areas, it's going to be greater than the area, that you were approximating, which is actually this area. So because the rectangles go above and beyond the region, we end up with an area that's greater than the actual area. And so this will serve as what we call an upper sum approximation, because it goes above and beyond the actual area under the curve. Okay, now in part C here, I'm going to change things up. Now I want to approximate the area under the curve using what we call an L4 left Riemann sum. So again, the 4 tells you to use 4 rectangles again, but this time I'm going to find the left Riemann sum. And so that means you're going to use the left endpoint of each subinterval to get the rectangle heights. So again, we're still going to break up the interval from 0 to 1 into 4 equal subintervals. So there's subinterval 1, subinterval 2, subinterval 3, subinterval 4. Okay? But instead of using the right endpoint of each subinterval to get the rectangle height, I'm going to get the heights by using the left endpoint. So again, watch this. Here is the first subinterval. If I take the left endpoint and I follow it up till it hits the curve, I get a y value of 0. So the first rectangle is actually flat. It doesn't have a height. Okay, again, that first rectangle does not have a height. It's flat. Okay, and then you go to your second subinterval. There's my second subinterval. Again, I'm going to use the left endpoint, follow it up till it hits the curve, and use that as my height of my second rectangle. Then I'm going to go to my third subinterval, and again, use the left endpoint, follow it up till it hits the curve, and use that as the height or length of my third rectangle. And then finally, here's my fourth subinterval. Use the left endpoint, follow it up till it hits the curve, and then go over and use that as the height of my fourth rectangle. So now, if you look at it, these are basically the same thing at this point. So what we're going to do now is we're going to take the area of that first flat rectangle, the area of that second rectangle, the area of that third rectangle, and the area of that fourth rectangle. I'm going to add up those four rectangle areas, and that's going to serve as a different approximation for the area under the curve. So again, if you look at those four rectangles, again, I'm going to find the areas by taking length times width plus length times width plus length times width. So for my first rectangle, which is flat, I'm going to use a left endpoint x value, which is 0, plug it into the function, which gives me 0 squared, which is 0. And then you're going to multiply it by the widths. Again, I want to make note that the widths are all still 1/4. Those are the widths. Okay? And then again, the first rectangle length or height comes from plugging the left endpoint of 0 into the function, which gives 0 squared, which is 0, and then 0 times a fourth gives me an area of 0 for my first rectangle. And then my second rectangle, clearly I'm going to use f of 1/4 as the height or length. So that gives me 1/4 squared, which is 1/16. And 1/16 times 1/4 gives me 1/64. And so on. So I'm just going to finish it up. I get my other rectangle areas, get a common denominator there, add them up, and I get 14/64. And by the way, if you change that to a decimal, you get 0.219 square units. And again, I want you to notice something here, that this approximation is less than the actual area under the curve, since the rectangles are inscribed or are inside the shaded region. So this will serve as what we call a lower sum approximation for the area under the curve. All right, so let's stop for a minute and read through this. Okay, so I just got 2.19 square units when I use the left endpoints. In part B, when I use the right endpoints, I got 0.469 for the approximate area under the curve. And so common sense should tell you that the actual area that we want under the curve is somewhere in between those two numbers. Okay? All right. There's one other kind of Riemann sum you need to know, and that would be what we call a midpoint Riemann sum. And so if you're going to find the M4 midpoint Riemann sum, once again, the 4 tells you that you can use 4 rectangles. And the fact that this is a midpoint Riemann sum means you're going to use the midpoint of each subinterval to get the rectangle heights. So again, you're going to take the interval from 0 to 1, split it up into 4 equal parts. Then you look at the first subinterval, and you take the midpoint, and you follow it up till it hits the curve and over to get the height of your first rectangle. And you do the same thing with the second subinterval. Take the midpoint, follow it up till it hits the curve, and use that as the height of the second rectangle. And so on. Here's the third subinterval. Take the midpoint, follow it up till it hits the curve, and use that as the height of the third rectangle. And then the same thing with the fourth rectangle. Okay, so again, we get that. So now I'm going to take these four rectangle areas I'm going to find those areas and add them up, and that's going to serve as another approximation for the area under the curve. So clearly, these are four rectangle areas again. The widths are still 1/4. And then the first rectangle length or height, as you can see, comes from what? F of, what's halfway between 0 and 1/4? An eighth? So you're going to take F of 1/8 to get the first rectangle height, right? And then multiply it by the width, and so on. Okay, the next one's going to be F of 3/8, right? Isn't that 3/8 right there? And so you're going to find F of 3/8 to get your second rectangle height or length, and so on. And then when you add all those up, you get that, which in decimal form is 0.328 square units. So this is a third approximation for the area under the curve. Now, all right, so let's start talking about what's going to happen now if I start changing the number of rectangles. Suppose I had used 5 rectangles for any of those approximations. Well, if you think about that, 5 rectangles would be a better fit for the area under the curve. And so you would have less, it would just be a better fit. So you'd have a better approximation for the actual area. If we had used 6 rectangles, again, 6 rectangles would fit nicer in there than 5 or 4. And so the approximation you would get would be even closer to the actual area under the curve. Because again, you'd have smaller rectangles giving you a better fit. So if you think about it, we can find the actual area under the curve by taking the limit of the rectangle sum approximations as the number of rectangles goes to infinity. So the more and more rectangles you use, the better and better the approximation. So if you take the limit as the number of rectangles goes to infinity, the area approximations will approach and eventually equal the actual area under the curve that we want. Okay. All right, we're going to do an application now based on what we just did. So if the function f of x that we are finding the area under, for example, is the velocity function with maybe units of feet per second, let's think about what the resulting units would be for our rectangle area approximation. Okay, so if you look at, remember, instead of f of x, I'm using the velocity with units of feet per second for the y values and seconds for the x or t values. If you look at one of those rectangles, the units here would be seconds, right? And then the units on the height of the rectangle would be feet per second. And so if you multiply the length times the width, you'd be multiplying feet per second times seconds, and in that case, seconds cancel, leaving you with feet. So what does that tell us? Well, since feet is a unit of distance, we can conclude that if we find or approximate the area under a velocity curve, the area represents the distance, or more specifically, the distance traveled on a time interval, time 1 to time 2. Okay? All right, so here's an example of this. And this is going to happen on the AP exam. You're going to be given nothing more than a table of values. Okay, so here's the problem that's given. So suppose the velocity of a moving car at 5-second intervals is recorded in the table. We want to estimate or approximate the total distance traveled by the car over the full 30 seconds using velocities at the end of each 5-second subinterval. So in other words, if you're going to split up 30 seconds into 5-second intervals, aren't you going to have 6 of them? So we'll be finding the R6 right Riemann sum. Okay? So now I want to emphasize you really don't need the graph. You really don't. But it does help to visualize the data points so you can visualize the rectangle. So all I did is plot these points. So I plotted 0, 6 right there. I plotted 5, 12 right there, and so on. And if you use the right endpoint, okay, because it says to use the end of each subinterval, so that's the right endpoint. So for this first 5-second interval, if you use the right endpoint and follow it up till it hits the curve, you get that first rectangle, right? Same thing with your second subinterval. Use the right endpoint, follow it up till it hits the curve, and use that as the height of your second rectangle, and so on. You're going to get 6 rectangles that look like that. All right, and clearly then, the widths of each of those rectangles are 5. Okay, so the widths are all 5. And then you can get the heights or lengths of those rectangles just by looking at the graph and the table. So for example, this first rectangle here has a height of v of 5, right? And so if you look in the table, v of 5 is what? 12. And so 12 is the first rectangle height there, or length. And then for the second rectangle, obviously the height is f of 10, or v of 10. And so if you look at the table, v of 10 is 14, isn't it? Okay, so that's where I get that 14 from. And you just keep doing this, okay? And then you can just finish it up, add those areas, and you get 615. And again, the units on that would be feet, because you're taking feet per second times seconds, which results in feet. Okay, so the total distance traveled by the car over the 30 seconds is approximately 615 feet. Again, it's an approximation because it's clearly not the exact area under the curve. It's only an approximation using these 6 rectangles. Okay? Now, note, you should see that due to the fact that the rectangles go above and beyond the region, in other words, they are circumscribed rectangles, the actual distance traveled would be less than this approximation that we just found. If we had used velocities at the beginning of each 5-second interval, the rectangles would have been inscribed, and thus the actual distance traveled would have been greater than that approximation. Okay? All right. Now here are some extra notes before I turn the page. Number 1, for example 2, if I'd given you the velocity function and use a graphing calculator, you could have found the right Riemann sum by entering v, the function for v into y1, and then on the home screen, all you would need to enter is y1 and put 5 in parentheses. That'll give you v of 5, and then times 5 plus y1 of 10, which gives you v of 10 times 5, and so on. Okay, and so you could easily find the Riemann sum on your home screen without really doing a whole lot on paper. Okay? Second thing I want to point out here is that if the velocity was ever negative, meaning the car was moving back in a backwards direction, then the area under the curve would represent displacement instead of distance traveled. Like, for example, you know, if it looked like this, you know, when you found, you know, when you find this area, it's going to be negative, so to speak, because the car would be traveling backwards that amount, and then the car would be moving forward this amount, which is a positive distance, so to speak. And so they would add up to 0. So that would not be distance traveled, that would be displacement. If the car went backwards this amount and forward this amount, it's right back where it started again. So its displacement would be 0. Okay, now, you guys, I'm going to kind of change subjects here for a few minutes, and then I'll kind of tie it all together. Okay, when we eventually find the exact areas under the curve, we're going to have to use summations. So we're going to have to review sigma notation, okay, which is used when we work with summations. All right, so when I write something like this, let's talk about what that means. The I equals 1 down here is the lower bound, and it means to start your sum with I equals 1. And then what you do is you keep adding 1. So you start with I equals 1, then you go to I equals 2, I equals 3, and so on. And you stop when you get to that number n. So that is the upper bound. And again, it means to stop when you hit I equals n. So what I'm going to do is this. I'm going to take whatever you see there, and I'm going to change the I to 1, and I'm going to write it down. And then the summation means you're going to add. And so I'm going to add what I get when I make the I a 2. So I'm going to get A2, and then you're going to keep adding. Now you're going to make the I a 3, and so on. And you're going to keep doing this until you hit n. Okay, so that's how we write out that type of a summation. All right, let's look at some more examples. How do I evaluate that sum? Well, again, you're going to take that, which is I, and you're going to replace I with 1, write it down, and then again, because this is a summation, you're going to add that to the next term. So the next term you get by changing I to 2. So if you put a 2 there in place of I, you get that. Then you put a 3 and a 4 and a 5, and you stop when you get to what? 6. And so if I add up all these numbers here, I'm going to get my answer, which is 21. So 21 is the value of that summation. Okay, let's look at another example. Look at this. So this time, my terms are going to look like this. They're going to be j squared. And so this time, it says to start j at 0. So if I replace j with 0 there, I get 0 squared. Okay, then you're going to add it to what you get when you make your j 1. So I get 1 squared. Then you make your j equal 2, and then your j equals 3, and you're going to stop when you hit j equals 4, because that's my upper bound on my summation. And by the way, what do I get here? 0 plus 1 plus 4 plus 9 plus 16, and so all that adds up to 30. So 30 is my answer there. Okay, now, next one. Notice what's happening. This time there's no I on my terms. But I'm going to still start with I equals 1. So when I equals 1, 5 is just 5. And then when I equals 2, 5 is just 5. When I is 3, 5 is just 5. When I is 4, 5 is just 5. And so I end up adding those up and I get 20. Okay? Next one. All right, so this time my terms are going to look like this. So I'm going to start out with I equals 1, so I'm going to put a 1 there, and I get this. Then I'm going to add it to what I get when I make I equal 2, and then make I equals 3, and so on. And I'm going to stop until I hit I equals n. Okay, so that just kind of gives you some practice on how to evaluate summations. All right, now, these are actually pretty easy. These are just properties of summations. All this says right here is that if k is a constant, you can pull it outside of the summation, okay? All this says is if you have a sum or difference inside your summation, you can split it up into separate summations and then just add or subtract those later, okay? All right. Now these are shortcuts, and the good news is I'm going to give you these on the test. Those will be given on the test, okay? So all you got to do is know how to use them. So for example, if you ever run into a summation that looks like that, okay, where C is a constant, and okay, the shortcut is just to take your C times your N, and that's going to be your answer, without having to go through all the adding. Okay, so for example, we can use that shortcut on example C above. So if you look back to example C here, right here, I'm just going to do it again using the shortcut. So there it is again. So instead of actually finding all the terms and adding them together, you can use the shortcut because it does fit, right? Doesn't this fit this form where you're just summing a constant like 5? So your answer should be your constant times your n, which would be 20. And sure enough, I get 20 using the shortcut. So I get 20 here, just like I got 20 when I did it the long way. Okay, so this is just a shortcut for finding a summation like that. Okay, here's another shortcut. If you ever run into a summation where you're just summing I from 1 to n, the shortcut is just to take your n times your n plus 1 and then divide by 2. So for example, doesn't this look like it would fit example A above? So if you look at example A, which was this, I just recopied it. Okay, so there was example A again that I just did a minute ago the long way. The shortcut would be, again, doesn't that fit the shortcut? And so the shortcut would be take your n times your n plus your 1 and divide by 2. And when you do all that, you get 21. And so 21 is the answer. And sure enough, isn't that what I got when I did it the long way a few minutes ago? So again, this is just another way. It's just a shortcut to evaluate a summation that looks like that. Okay, and then if you ever run into a summation that looks like that, you can just use that shortcut. If you ever run into a summation that looks like that, you can use that shortcut, and so on. Okay, so let's do an example. Okay. So for example 4, suppose I want to simplify that. Okay, well, the way it is, it doesn't fit any of these shortcuts. But I can break it up using the properties that I was just showing you a minute ago, these properties 1 and 2. So watch how I can break this up. Ready? I can break it up into the following. If n is a constant, which it is, then n squared is a constant, and I can just pull it out. So what I did is I pulled the n squared out front as a 1 over n squared. So again, if I pull the n squared out of there, I get 1 over n squared, and that leaves me with the summation of I plus 1. Okay? Okay, all I did was pull out the n squared. Now, this can be broken up using, again, the summation property up here. So what I can do is I can break that up into 2 separate sums like that. Okay, so I can break it up into the summation of I plus the summation of 1. Okay? Now, at that point, I can use one of the shortcuts on this. Okay, so when I have the summation of I, can't I just use shortcut number 2 and replace it with n times n plus 1 over 2? So that's what I did. And then when I have a summation of a constant like 1, doesn't that fit property 1 here? And so what I can do there is replace that with your c times n, so 1 times n. Okay? And then from there, it's just some algebra 1. So what I did is I distributed the n here, and then I got a common denominator to bring these together under one fraction like that. And then I just multiplied these two fractions to give me that. Okay, so at this point, what I've done is I've turned this into this. Okay, so I can now replace that with that if I want to. Okay. Oops, I'm sorry, guys. Let me say that again. Yeah, I started out with the summation of I plus 1 over n squared, okay? And I turned it into actually that, okay? So again, I just turned that into that is all I've done so far. Okay, guys? All right, next page. Okay, last page. All right, now part B, I want to start all over. And notice that part B says take the limit of what I just did in part A, right? So part B says take the limit as n goes to infinity for that summation that I was just working with in part A. So again, I'm taking the limit of this. And in part A, didn't I just find out that that can be replaced by all of that? So now I'm going to take the limit of that as n goes to infinity. And again, I can just use my old shortcuts, right? We have a polynomial over a polynomial with the same degree. The limit as n goes to infinity would be found, since these have the same degree, wouldn't I just take leading coefficient, which is 1, over leading coefficient, which is 2? And so taking leading coefficient over leading coefficient, I get a limit of 1/2. Okay? All right. All right, now I'm going to tie all this together. And so to do that, let's go back to something like example 1. Okay? So let's start generalizing. So instead of using 4 rectangles, right, for the area under the curve, suppose I just use n rectangles. Okay? And by the way, get used to this delta x. We're going to typically use delta x for the width of these rectangles, okay? And I kind of talked about this on page 1 of my notes, but you can get the width of each rectangle, delta x, by taking the whole interval length, just by taking b minus a, that'll give you the whole interval length, and then dividing by the number of rectangles n, and that will give you how wide each rectangle is, or each subinterval. Okay, now, what I want to do is I want to write general expressions for the right endpoints. Okay, and so if you look at it, for my first rectangle here, the right endpoint will be x of 1. Now, how do I find x of 1? Well, think about it. I'm starting at A. Right here, this is A, and I'm adding 1 rectangle width. So I'm starting at A, and I'm adding 1 delta x, okay? Another way you can look at it is, you're starting at x of 0 and adding a delta x, same thing. Okay, now how do I get the second rectangle right endpoint? So how do I get the right endpoint there for my second rectangle? Well, again, look at it. You're starting at A, and then you're going over 2 rectangle widths. So to get the second right endpoint, you're starting at A, and you're adding 2 delta x's. And then to get the third right endpoint, you're going to start at A and add 3 delta x's, and so on. Okay, until you get to the n. Okay, and so at that point, the ith right endpoint can be found by taking A plus your I times your delta x, if you see the pattern. Okay? All right, so we can now write the right Riemann sum approximation for the area under the curve. Again, remember, this is the right endpoint. On this whole thing, I focused on the right endpoint, didn't I? Okay. So you can get the approximate area by taking the rectangle lengths times width. So again, the delta x's are your widths for each rectangle. And then obviously this is your first rectangle height, your second rectangle height, and so on, right? Your third rectangle height until you get to the nth rectangle. So again, this is just adding up a bunch of rectangle areas. Length times width, plus length times width, plus length times width, plus length times width, and so on. Okay, now, what I'm going to do is I'm going to use sigma notation to rewrite that. So instead of writing those out like that, can't I just turn that into the summation, starting at 1, I equals 1, and ending at n? Okay, so there's just another way to write that. And then finally, using the fact that I mentioned earlier that the actual area, not the approximate area, the actual area can be found by taking the limit as the number of rectangles goes to infinity. We can take this, which would have been an approximation, and take the limit of those approximations as the number of rectangles goes to infinity, and that will turn the approximation into the exact or actual area. Okay? Okay. And so there it is. So now, if you use this whole formula, you will get the exact area under the curve. And by the way, the textbook refers to this as definition number 2. Okay? Yeah, when you're looking at the homework, if it mentions definition 2, that's what it's talking about. Okay? All right, now here's what I want to say. And then we'll do one last example, and that'll be it. Although the summation would be different if I had used the left endpoints or the midpoints or any other point in the subinterval, once I take the limit as the number of rectangles goes to infinity of any of those other possible summations, we would always end up with the same exact area under the curve. Okay? And so since it doesn't matter if we use left endpoints, midpoints, or right endpoints, I'm just going to tell you that it's going to always be easier to see if you use the right endpoint like I did here. Okay? All right, so let's do an example, and that'll be it. It says find a limit expression for the actual area under this curve from 1 to 3. So the first thing I'm going to do is draw a sketch. So I'm just going to graph that, which is y equals square root of x. So just plot some points. When x is 0, you get a y of 0. When x is 1, you get 1, right? Square root of 1 is 1, right? If you plug in a 4 there, what's the square root of 4? 2, so you get the point 42. All right. So all I did is graph the function. Now, I want to talk about the actual area under the curve between x equals 1 and x equals 3. So that would only be this area right here from 1 to 3. Okay, so I only want to talk about that area right there. Okay, so I want to find that exact area right there under the curve from 1 to 3. So to find the area of that shaded region, and again, this is going to be the exact area, not an approximation, we're going to start by finding our rectangle widths, or delta x, by taking b minus a over n. So I'm going to do 3 minus 1 over n, which obviously equals 2 over n. Okay? All right, so there's my delta x. That's the width of any rectangle. Now again, using this formula from earlier, again, if you remember, that formula right there will give you the right endpoints, won't it? Okay, so using that formula now, to get my right endpoints, this is what I get. X of I equals A. What's my A in this case? Well, I'm starting at 1, so my A is 1. And I'm going to add I times my delta X. Okay? And by the way, that simplifies to this. Okay, so there's my right endpoints. Okay, and so if we want to write an area expression, okay, again, I'm just going to use this formula. This will give you the exact area under the curve. And so I'm going to take the limit as n goes to infinity of the summation from I equals 1 to n of f of x of I. Again, now be careful. F of x of I is just this formula plugged into the function. So I'll be plugging in my x of I, which is 1 plus 2i over n, into my square root function. And then I'll be multiplying that by my delta x. And so my delta x is 2 over n. Okay? Now, we're not going to finish this today. That's actually what we're doing next time. But if we were able to finish and find this limit, that will give me the exact area for that shaded region right here. Okay, so again, for today, if you get to there, that'll be good. And then I'll show you how to finish something like this next time when we get to section 5.2. Okay? All right, so you're going to have a variety of homework tonight. So look back through my examples if you need to, and you should be able to get the homework.